This lesson's on permutations, but you started that yesterday, so hopefully it worked okay for you. This is a rule, a structured rule for permutations. In other words, order is important. As opposed to combinations. Now, we also talked about 0 factorial equaling 1, which is important. We didn't mention that npn equals n factorial, so we'll prove that quickly. So npn, using the rule up here, is n factorial over n minus n rather than n minus r, because you've got n equals r factorial, which is n factorial over 0 factorial, and because 0 factorial is 1, it proves it. So anyway, that's what we're starting with. Okay, well, I do want you to get on the questions pretty quickly, so we'll get into these ones. I looked through the questions that we want you to be able to work on, and they do have a bit of thinking involved. So I thought it was worth doing a video just for these permutations stuff. I'm going to be doing the examples that are from the textbook just to make it a little bit more easier to follow. Now, the first one's a bit of a no-brainer because I've already talked about this. How many ways can you arrange 6 people around a table? So if you have 1, 2, 3, 4, 5, 6 people sitting around a circular table, we know that the first person can actually sit anywhere. So just using the fundamental counting principle, we can say that the first person can sit anywhere. So let's say they sit here, and then the next person can sit in any one of the 5 seats, and then the person after that can sit in any of the 4 seats, right down to 1. So we already know that that's how this works. You know, 1 less than the number of people factorial. So that certainly makes it nice and easy, which is 120. But we haven't dealt with any questions where some restriction happens like this. So if you've got 6 people sitting around a table, this is using the same scenario. If they're seated at random, what's the probability? So we better tie a little bit of probability into this, that 3 people sit together. So whenever you do this, this is for today and tomorrow, when we talk about combinations, it's the same, join them. So in other words, instead of having 6 people, A, B, C, D, E, F, think about, if you're talking about A, B and C being together, think about joining them together as one group. So that's like one person. So how many objects do we have? 1, 2, 3, 4. We have 4. 1, 2, 3, 4. So 4 objects. And seat them around a table. Now, if you're sitting 4 things around a circular table, you can do that in 3 factorial ways. Okay, that's fair enough. Now, what about if they are around the table? So you've got A, B, C together, and then D, E, F. How many ways can those 3 sit together amongst themselves? Because this is just the number of ways you can seat 1, 2, 3, 4 things around a circular table. How many ways can you sit them amongst themselves? And of course the answer to that is 3 factorial. So, how many ways in total can 3 people sit together if they're randomly seated out of 6? So total, 3 factorial for the number of ways you can sit 4 things around, times 3 factorial for the number of ways you can sit the people amongst themselves. So that's 6 times 6, that's 36. Now, what do we do with that number? It's a probability question. The way the probability questions work nicely is that you put on the, or we'll just write probability of 3 people together is the total number of ways they can sit together over the total number of ways they can sit. So the total number of ways they can sit together is 36. The total number of ways they can sit, period, is 120. So it's 36 over 120, which is 3 in 10. There's some questions like that in the textbook. Next, how many ways can the letters be arranged. These are classic questions. So the first one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 letters, and you can arrange them amongst themselves 11 factorial different ways. Now the problem is, let's have a look, there's 2 E's, and the E's are the same. So because there's 2 E's, there's actually not 11 factorial different letters, different words that you can do if you put all 11 of them down, because whether the first E's there and the second E's there, or they're swapped around, it's exactly the same word. So there's 2 times too many, so you just halve that. So that equals a lot, 19,958,400. But just to be complete, you actually should say 2 factorial, because that will work for the larger numbers in exactly the same way. And hence we have this Parramatta. So exactly the same idea, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10 factorial ways that they can go down together without restriction over, now how many P's are there? 1 P, how many A's? 1, 2, 3, 4, 4 A's. So for the 4 A's, you divide it by 4 factorial. How many R's are there? 1, 2 R's. Oh, 2 R's. And what else? We've got 2 T's. So 2 factorial for the 2 T's, and that should be it. Yep, that's it. So we'll just have to use a calculator for this one. Don't have this answer. So 10 factorial, I mean, you're pretty sure you're okay with the buttons. 10 factorial divided by, in brackets, 4 factorial times 2 factorial times 2 factorial, or I suppose you probably use your fraction button, works the same way. 37,800. Now, I'm running out of time, so actually I knew this would happen, so I want you to look through example 12 yourself. I will put the textbook copy here just so you can have a quick look at it. I'll just put it under here. So this is what I'm talking about. Have a look at 12 yourselves, because it does have some restrictions on it. Follow it through. Makes sense, the explanation is actually really good. And then work on exercise 3.04, and again I'll just take turns to put the whole textbook on there so you can use the video rather than necessarily have to move the textbook out. So there's some really wordy questions, so those of you who didn't like the problem solving, gonna have to worry about that. So yeah, do 5, 7, 9 as much as you can through to 29.